Welcome to Module 1.4 of EF5 training from the University of Oklahoma's Hydrometeorology and Remote Sensing Group. My name is Trace Clark. Thank you for joining me. This topic is going to be DEM derivatives. So we're now at the end of the day one modules of the EF5 training. If you haven't gone through and watched the videos for the welcome session, the introduction to hydrological modeling, or the EF5 overview, we recommend that you go through and watch those first in order and then return to this module before continuing. But if you've already completed those three and you're ready to start, we're going to be talking about various pieces of topographical information in this particular module. So topographical information is a key component of any hydrological model. It tells the model how the Earth's surface behaves. It tells the model where the ridges and valleys are, where the mountains and hills are, where the rivers and streams are, and where any other important hydrological features exist. Without topographical information, it would be impossible to route water downstream or to produce any forecast of stream flow or soil moisture. So topographical information is absolutely critical to any hydrological modeling endeavor. It takes many different forms, but in EF5, we're going to be talking about three specific pieces of information. Those are the DEM, which stands for Digital Elevation Model, the FDR, which stands for Flow Direction, also called a DDM within EF5, and the FAC, which stands for Flow Accumulation, or FAM in EF5. These always follow a specific order. You always start with a DEM, you create the flow direction map from that, and then you create the flow accumulation map in your last step from the flow direction map. So that process works only in that direction. You can't generate an FAC and then go backwards. You always start with a DEM, then the FDR, then the FAC. So what is a digital elevation model? Well, the digital elevation model is a model of the Earth's surface created from terrain elevation data. It's stored as a grid of numbers. Each grid cell has one number, and that number is the elevation of the grid cell in the units of the DEM. That's typically in meters, but it could be in kilometers or centimeters or whatever else if you were feeling particularly weird that day. And these grid cells match exactly with the EF5 model grid cells that we discussed in Module 1.3. And down at the bottom of this slide, we have actually an exaggerated view, an example of DEM, that shows how the various ridges and valleys and streams are represented digitally within the DEM. We all know that water flows from high points to low points. That's just a consequence of gravity. And so if we have a DEM and we give that DEM to a hydrological model, the model now knows how water flows and where water flows across the entire domain. And so in the cartoon on this slide, the columns are like that exaggerated DEM that we saw on the last slide. The arrows mark the directions of the flow of water, and the blue arrows, in this particular example, are collecting a lot of water from upstream cells. They have a lot of cells that contribute to them, in other words. And so we think of them as sort of the main river channel. The red areas have less contributing area. There's less cells that are flowing into those red cells, and so we think of those as overland cells. And so that's an important distinction in the hydro model between the overland cells and the river cells. So how is a DEM created? If the area is small enough, it might be created by a direct survey. So you might send people out and they might measure the elevation at many different points and create a DEM from that information. But usually we're dealing with larger areas, and so it's cost prohibitive or time prohibitive to actually send people out and directly create the DEM through survey techniques. And so instead we use remote sensing. The Earth's surface can be scanned from space to create a DEM. And this is oftentimes done via radar satellite from space. And so some examples of that technique include RadarSat, SRTM, and ASTER. One of the most important characteristics of the DEM is the resolution of the DEM, or the size of each individual grid cell. So on this particular slide, I have two DEMs of the continent of South America. One of these is at 4 kilometer horizontal resolution. So in other words, each grid cell is 4 kilometers by 4 kilometers in size. That DEM takes up about 5.2 megabytes on a computer hard drive. The other DEM is at 30 arcsecond resolution, which means that at the equator, each grid cell is about 1 kilometer on a side. And that DEM takes up 36 megabytes on a computer hard drive, so 6 or 7 times as much space. And at this resolution, when you're looking at the continent, is it possible for you to tell the difference visually between these two maps? For most people, it's probably not. So let's zoom in a little bit farther and see if anything changes. Now, if you look in the Amazon region or the Amazon Delta of South America, you start to see some differences. On the left, where I'm circling with the mouse, you see a lot more details showing up in the river network. On the right, you don't see all of those details, and so the map on the left is 30 arcsecond DEM, the larger DEM. The one on the right is the coarser, smaller DEM. If we zoom in even farther, the differences start to become extremely obvious. Now, the map on the left, the one that's less detailed, it actually starts to look pixelated or grainy along the coast of South America there on the Atlantic Ocean, whereas the higher resolution DEM still looks extremely smooth and natural. And so now we're starting to see that there really is a difference in what the resolution shows. So this exercise demonstrates a few important points about resolution. In general, the larger or more spacious the model domain is, the coarser the resolution can be. Hydrologic models require computing power, and the number of cells being modeled is directly related in general to the computing requirement. So a higher resolution DEM means you have more model cells, which means that the model is going to take longer to run. So the number of cells being modeled, that of course has to increase as that resolution increases. And running large areas at high resolution requires either fast computers or more time to complete the model run. Now let's move on to discussing flow direction grids. Flow direction grids, or FDRs for short, are grids that contain values that tell you where water is flowing. So let's imagine taking our DEM cartoon from earlier, and we're basically going to tilt it toward the camera so that we're looking at it from basically directly up in the sky, downward at the Earth's surface. When we look at it dead on, now we have a grid. It has the same size, resolution, and extent as the original DEM. But now those arrows, we can see them from head on. We can see them directly. And this grid exists to tell me now in what direction water is flowing across my domain. But a computer can't necessarily understand those arrows in a very easy way. So instead, computers like numbers, and so we're going to assign a number to each cell within that domain. And this is called a coding scheme. There's different ways to do this. The scheme I use is basically the 1 through 8 scheme, or the V8 flow direction scheme. It's also the scheme that's used in the TAUDIM program that we're going to be using throughout the training. But there are other schemes out there. If you're familiar with the Esri ArcGIS suite of products, their ArcMap program actually uses a different scheme. Rather than going 1 through 8, it goes 1, 2, 4, 8, etc., on up to 128. And what's important is that each number corresponds to a flow direction, and then once you put all of those numbers together, the computer can use that information now to tell you where the water is going to flow. You probably noticed, if you thought about it a couple of seconds, that some of the cells flow into 2 or more other boxes. And so when that's the case, if you have one cell that flows into 2 cells, but you can only assign one number to that cell, you have to decide which number gets picked. And so the way that the computer picks the number for that cell is the elevation difference. So the steepest descent or the steepest angle of flow is the one that wins out. And so that's the one that gets its number voted into the final flow direction map. This is called the 8-direction flow model, or D8 for short. Some important things to keep in mind when using the D8 model. Your DEM needs to be larger than the river basin you want to model. In other words, you need to have some buffer space around all of the edges of your river basin. And that's because the outer edge of flow direction cells will not actually have values in the real world. And so that's because the computer doesn't know what's beyond the edge of your DEM. It can only start calculating flow direction inside your DEM. So that's why you need your DEM to be larger than the area you're eventually going to model. So the third and final necessary component of all this is the flow accumulation, or FAC for short. The FAC is a grid of numbers that corresponds to the number of cells flowing into that cell. So just think about that for a second and look at the cartoon at the bottom of this slide. You'll notice in the upper left corner of the cartoon, the upper right corner, you have a value of 1. And that's because those cells are relatively high to everything else around them. So nothing flows into them. The only thing contributing to the flow in that cell is that cell itself. And so it gets a value of 1. As you start to move downstream, you're starting to add up all of the cells up above that are contributing to that, and your numbers gradually get larger and larger and larger. If you follow everything down to its logical extent, down at the bottom center of the cartoon, you see the number 36, and we're dealing with a 6x6 grid. 6 times 6 is 36, and so all 36 cells are flowing into the mouth of the river, basically at the edge of the flow accumulation curve. Note that in this case, all of the flow accumulation cells with a value of 5 or greater are highlighted in blue. So when we first started discussing DEMs, we mentioned with the arrows that some of the cells had more arrows flowing into them than others. and we highlighted those with lots of flow in blue. We also briefly mentioned the TH parameter, which is short for threshold, back in module 1.3. And so that parameter, that threshold parameter, is the threshold for a river channel cell. So here, for this example, our threshold parameter in the model would be 5. And now anything that has a value of 5 or greater in the flow accumulation map becomes a river cell. Anything with a value of less than 5 becomes an overland cell. So where do we get the DEMs that are needed to make all of this cool stuff? Well, we're lucky. There are several free, good quality DEM sources around the world. Some of them are worldwide, some of them are continent-wide, some of them are countrywide. But we're going to focus our discussion on probably the most well-known of these data sets and the most freely distributed. And those come from the Shuttle Radar Topography Mission, or SRTM for short. So this was actually part of the mission STS-99, launched back in February 2000. We actually have a picture of that shuttle mission itself landing on Merritt Island, Florida in February 2000, and then the mission badge for the people that actually ran the space shuttle for this project. And what they did is they basically used a radar instrument to scan most of the Earth's surface. Some of the characteristics of the SRTM data, they're available around the world at 3 arcsecond resolution, or 90 meters on each side of a grid cell. The original SRTM data, also known as SRTM1, have been processed and corrected for hydrological use around most of the planet. And so one great source for this is the HydroSheds program. That's a screenshot of their website at the bottom of this slide. HydroSheds is funded by the World Wildlife Fund, or WWF for short, and so they provide continent-wide or subcontinent-wide DEMs, drainage directions, and flow accumulation grids at specific resolutions. They also have river networks, drainage basin outlines, and some other useful hydrological information. Their website is hydrosheds.org. So again, it's all freely available. You're highly encouraged to go check it out. We actually use HydroSheds data for many of the examples within the EF5 training. Now, more recently, the SRTM data has actually, or SRTM2, which is the original 30-meter resolution, so a greater resolution than the original 90-meter resolution, has been released for all of the planet as of November 2014. And so we'll discuss specific applications of the higher resolution SRTM2 data toward the end of EF5 training. But for right now, we're going to focus on the coarser resolution, older SRTM1 data set. So as part of the EF5 training course, we include the necessary river networks and DEMs for certain model examples. The way the file names work is each one starts with the word example, then the number of the example, underscore, and then the type of information, .zip. So example2 DEM is a zip file that contains all of the DEM information necessary for example2. Example2 rivers.zip is a zip file that contains all of the rivers for example2. The DEM quality is very good, but it's not perfect. They're just when you're dealing with something as large as the surface of planet Earth, there are naturally going to be some things that you don't necessarily notice. There could be some errors involved. And so just keep that in mind as you're using the HydroShed data set. The river network files are in Esri shapefile format. The DEMs are in the Esri grid raster format. Either of those can be opened in either Esri ArcMap or in QGIS or in any other piece of GIS software. There's some other sources available too. The GTOPO 30 project at USGS, the United States Geologic Survey. That's a 30 arcsecond or 1 kilometer world DEM. It's also derived from SRTM. So again, we're starting with the same base data set, the same SRTM information. It was just processed slightly differently, and so that's what the difference between GTOPO 30 and the HydroSheds data set is. The raw SRTM2 data was collected at 1 arcsecond or 30 meters, so 9 times the size of the finest HydroSheds SRTM1 DEM. And again, until 2014, this 30-meter data was only available in the United States, but it has now been released to the rest of the world. It's called SRTM2, and again, we'll talk about that more later in the training. So let's dive right into example 2 again. I'm going to be starting in the country of Colombia. We're going to process our own DEM files. We're going to create our own FDR and FAC, and we're going to eventually use all of that inside EF5. So we're going to be talking about the Bogota River Basin in Colombia, and we're going to be upstream of a gauging station at Puente Portillo. So to get ready, we're going to just move some files around and get things in the right places so that we're ready to start. All right, let's go ahead and get started with example 2. So we're going to just start by moving some files into place and getting everything ready to go. So on my desktop, I'm going to go to my EF5 training folder. Remember, we want the unzipped version of the EF5 training. And I'm going to go ahead and navigate to my examples folder first. And you'll see I have two folders here, Wang Chu, which was example 1 that we already ran, and I have a folder called example 2 that's already ready to go for me. When I go inside example 2, you'll see I have basic, OBS, output, PET, precip, and QGIS. So I'm going to go ahead and go inside this QGIS folder, and there's nothing going on in there right now. So we're going to fill up that QGIS folder with all kinds of processing information and data sets that are going to get us ready to run the model. So on the next slide, I want you to go back into EF5 training. This time you're going to go to data, and you're going to go to HydroSheds. And inside HydroSheds, you should see 6 files. The 4 down at the bottom are from the very first welcome module where we tested out QGIS. If you remember, we opened up SDEM, and then we did the pit remove process on it to test that how it was actually installed. We saved that file as fixed DEM, and then those .aux.xml files associated with it, those are used by QGIS to help enable fast loading of the data sets in future times. But at the very top, you'll have 2 zip files, example2 DEM and example2 rivers. So let's start with example2 DEM. You're going to right-click it. You're going to go down to Extract All. Now, if you have 7-zip or WinRAR or another uncompressed utility installed on Windows, it may be called something slightly different. But for those with just the default basic Windows, it'll say Extract All. And a little dialog box will pop up, and it'll ask you what folder you want to extract the files to. So I'm going to go to Browse, and I'm going to start from my desktop, EF5 training. And then I actually want to put this inside my examples folder. So I'm going to go to Examples, Example2, and QGIS. I'm going to click OK, and now you'll see in my dialog, or in my little text box here, it says EF5 training, examples, example2, QGIS. And it also says show extracted files when completed. I'm going to go ahead and leave that checked. I'm going to click extract, and I get another window that's popped up, and it now has example2 DEM and info. And if I go down inside example2 DEM, I see a whole bunch of different data sets. But the really important one is this W001.001.adf. And the reason I know that that's the important one is that the file size is pretty big. It's 35 megabytes, and everything else in this folder is less than 500 kilobytes. So I'm going to go ahead and exit this new window that popped up. I'm going to go back to my HydroSheds folder, and this time I'm going to unzip example2 rivers.zip. So I'm going to right-click, go to Extract All. I'm going to click on Browse. I'm going to look for EF5 training, and I'm going to go to Examples, Example2, and I'm going to select QGIS again. So this should be the same exact folder that you unzipped the DEM to. So this is going to be EF5 training, examples, example2, QGIS. And I'm going to click extract. And it'll take just a second. And now my QGIS folder reappeared. And this time I have the 2 folders I had before. And now I have an additional 8 files. And so on this one, the important file is, again, the big one, the .shp or .shapefile. So example2 rivers.shape is actually a shapefile or a vector file that contains the river networks for our area of interest. So now we're ready to actually get started. So just make sure that your QGIS folder looks the same as mine does on screen right now. And once it does, you're going to go ahead and go to your desktop and open up QGIS Desktop 2.6.1. And so QGIS takes a second to get all of the environments set up and everything and ready to go. But once it opens up, you should have just a big blank screen like I have right now. And you're going to go to the top of the screen and click on the Layer menu. You're going to go to Add Layer, and the first thing we're going to do is add a vector layer to our project. So we're going to make sure that we're going to browse for it. We have to make sure we're in the right spot. Now, QGIS normally starts by searching in this QGIS folder, and we don't want to deal with that QGIS folder. We want to make sure it's our QGIS folder. So we're going to go to Desktop, EF5 Training, and then you're going to go to Examples, Example2, QGIS. And we're going to be adding a vector file, not a raster file. So a vector file is something that has lines in it. It could have polygons, points, polylines. It's something like our river networks. It's not a grid. A grid would be a raster. So we're going to just look at vector files right now. So we're going to open example2rivers.shp. And I'm going to click open again. And you should see something fairly familiar. You should see the continent of South America. And if you want to explore this file a little bit, at far range, when we're zoomed out, it looks just like solid land. When we start to zoom in, now you see all types of little tiny river networks. So this is our river network shapefile. And I'm going to go ahead and zoom back out. So I'm going to click this little magnifying glass that has 3 blue arrows pointing out from it called Zoom Full. And when I do that, I'm back to South America again. Now I want to add a raster file. I want to add my grid and my DEM. So I'm going to go back to add layer. And now I'm going to go to add raster layer. And this time, now this time it opens up to my desktop. So QGIS is now getting smarter. It's knowing where we're looking for files now. We're going to go to EF5 training, examples, example 2, QGIS. And this time we're going to go inside our example 2 DEM folder, and we're going to open up that big file, the one that has a greater file size than any of the rest, called w001001.adf, and we're going to click open. And again, you see South America, but now it looks a little bit different. Now you're seeing black and white, and this is a DEM, so this represents elevation. So the areas in white, those are the Andes Mountains. That's where you see extremely high elevations. The areas in black, that's low elevation, so that's the Amazon basin and the other plains across most of the rest of the continent. So at this point, now that we have these files loaded, just for good computing practice, we're going to go ahead and save our project. So we'll be using this project for the rest of the example. So you want to go to the project menu at the very top left of the window, and then go to save, or you can use your keyboard and click Control-S. And when I go to save, I don't want to save it in this binary or bin folder. I want to go to my desktop, EF5 training. I'm going to go to examples, example 2, QGIS. And you can save it whether you want, but I'm going to call it example2.qgs. And that's just a QGIS project file. So now I click save, and at the top of my window, at the menu bar, it now says QGIS 261 Brighton-example2. So that's telling me that I've saved my project. So the first thing we need to do is actually one of the most difficult things we're going to do during this module, but don't worry, we're going to go through it together step by step. We're going to add our location of our gauge to our map. So our gauge, if you recall, is named Puente Portillo, and it's on the Bogota River in the nation of Colombia. So we want to add a point at the exact location where that gauge is on the river, and then we're going to draw some boxes and do some other things based on where that gauge is located. So since the gauge location is sort of the first thing we're doing, it's also the most important thing we're going to do. We have to get it right so that everything downstream from this and after this will work properly. So the first thing we're going to do is create a new shapefile layer. So we're going to go back to our old friend, the layer menu. This time we're going to go to create layer, and it's the first option, new shapefile layer. And a dialog box pops up called new vector layer, and it's going to ask me what type. So I have 3 choices, point, line, or polygon. We're going to pick one location for the gauge, so we just need a point. It's going to ask some things about file encoding and the various coordinate reference systems and other things. We're not too worried about any of that. We can keep all the defaults in place for all of that. We're going to leave everything else alone, and we're just going to click OK. And when we do, a dialog box pops up and asks us what we want to save the layer as. And you'll notice that it says save as type Esri shapefile.shp. So we're going to create a shapefile. And you can call it whatever you want, as long as you remember what it's called. But for consistency's sake with PowerPoint, I'm going to call mine gauge_LOC, which is short for location, .shape.shp. And I'm going to click Save. And now, over at the left, in the Layers panel of my QGIS window, I have a new layer that's appeared. It has a little purple dot, and then it says Gauge Location. And we want to edit this file because right now the gauge location is totally blank. There's nothing in it, and we want to add a gauge location to it. So the way we're going to do that is up near the top left, you'll see a pencil in yellow, and if you mouse over it, it'll say Toggle Editing. We want to turn on editing, so we're going to click. And when we do, you might not have noticed anything changing immediately, but some of these icons down the second toolbar appear. They suddenly appear, they change from gray to brightly colored. So that's telling us that we're in editing mode. You'll also be able to see that there's now a pencil over the little purple circle next to gauge location in the layers window. So that's another way that you know that you're in editing mode. Now you're going to use the coordinate box at the bottom of the screen. You'll notice as I move my mouse around, the numbers in there change. That coordinate box shows the latitude and the longitude of the exact point where you're currently located. So for this gauge location, I've already done the work to tell you that it's located at 74.6 degrees west longitude and 4.45 degrees north latitude. Or in other words, negative 74.6, 4.45. So I'm going to use the coordinate box, I'm going to use my mouse, and I'm going to use the zoom function to zoom in on that part of South America. So we already know that Colombia is near the northern part of South America, so let's zoom in to the north first. That gives us a general idea of where we should be. And then I'm going to kind of move my mouse around and see where I'm supposed to be. And I'm going to look at the ridge of white area, or the ridge of higher elevation up near the top left of the map of South America, because that's the general area in which I want to be located. And so as I zoom into that, and I move my mouse around, it turns out that I really want to be somewhere on the left edge of that first ridge, or in between the two ridges, in between the two white areas. So I'm going to zoom in again. And now it starts to get a little trickier, because now I don't have any other references to tell me where I am relative to the coast or anything like that. All I really have is the coordinate window to rely on. Another interesting thing is that as I start to zoom in, the coordinate window is more and more precise. I'm now seeing more and more numbers after each decimal point. So that's, as you get closer and closer, you'll be able to move the mouse more finely to get more accurate results about exactly where you're located. So I'm going to look around for 74.6 as I move my mouse from left to right. And as I move my mouse up and down, the second number, the latitude, changes. And in this case, we want to go a little bit farther south on my window. And so I feel pretty confident about where I am, so I'm going to zoom in again. And now I can start to see individual pixels. I can actually start to see the true resolution of my DEM. And now I'm zoomed in so far that I'm seeing 4 decimal points after each number in the coordinate window. So now I feel pretty confident that I'm ready to start dropping my exact point where the gauge is located. So once you're satisfied with how you've zoomed in, you're going to click the Add Feature button. So you're going to go back up to the toolbar, the second one from the top, and the fourth button from the left has a little, it looks kind of like a yellow snowflake, and then there are 3 green dots around it. It's called Add Feature, and I'm going to click that. And when I click that, now my mouse on the screen looks a little bit different. It's probably hard to see on the video, but on your own home computer, you'll be able to see it quite clearly. Your mouse cursor actually turns into a bullseye, or a target. And that's telling you that wherever you click, now there's going to be a target right there. It's going to put a new point there. So I'm going to look for negative 74.6, and I'm going to look for 4.45. And you don't have to be absolutely perfect with this, but you want to get as close as you can. And now I'm going to click. And when I click, a little tiny window pops up that says Gauge Location, Actions, ID, and then there's a blank little text box in it. So it doesn't matter what you put here. I'm just going to put ID1, and I'm going to click OK. And now there's a purple dot exactly where I clicked. Now I'm going to click the pencil back above the Layers pane, and I'm going to basically turn off Toggle Editing. And when I do, it asks me to stop editing. Do you want to save the changes to the layer? And if I'm satisfied with where I place the point, which I am, I'm going to click Save. Now you'll notice that all of those buttons that are at the top turned gray again. The pencil is gone from Gauge Location, and I have a purple dot where my gauge is located. So let's take a brief second to review what we've done so far and why we've done it. We set up our QGIS project. We extracted the DEM and the river network into our project folder. And we created a shapefile that contains one feature, a point at the exact location where our river gauge is located. These 3 pieces of information are the initial pieces that we need to do everything else within the module and to get the GIS portion of EF5 ready to run. So the next step is going to be to identify the basin extent, or to identify the edges of our model domain. So now in the layers pane, you're going to drag example 2 rivers in between gauge location and the W001001. And your screen will immediately change. Now you can see rivers on top of the DEM, and you can also see your purple gauge point that you just created. I'm still zoomed in, so I'm going to zoom out a little bit. And I'm also going to change the color of my river shapefile. So right now mine is yellow. QGIS tends to do this somewhat randomly, so yours may be red or green or blue, but mine is difficult to see. So I'm going to right-click and go to Properties. And under Color, I'm just going to pick red, because I think that's easier to see. Maybe red isn't the best choice. Let's try Bridleway. That's much easier to see. I'm also going to right-click on my gauge location, go to Properties, and I'm going to change the size from 2 millimeters up to 6 millimeters, just so that you can see it better. And again, if you don't want to do that part, you don't have to. This is just to make things, for me, easier to see. I'm going to zoom out one more time. And now you see all that kind of ugly green stuff, a big purple dot over it, and then the DEM or the elevation back behind it. So now I'm going to do something called selecting features using an expression. And the way I'm going to do that is by going up to the top toolbar, and I'm going to go to the yellow box with the purple E beside it, and I'm going to click that. And when I do, I get a new dialog box called Select by Expression. And in the expression box, I'm going to type up underscore, and I did realize I made a slight mistake. So you see it says Select by Expression Gauge Location. I actually want to make sure I've selected my river file first. Now I go back to Select by Expression. It says example 2 rivers. I'm going to type up cells, so up underscore cells. And then I'm going to type a greater than sign. And when I type that greater than sign, you'll see down at the bottom it says output preview, expression is invalid in red. So this is actually like a mathematical equation. We want to select all of the rivers larger than some threshold. So I can type whatever number I want at first, say 300, and then click select. And when I do, at least in my case now, the rivers larger than 300 are highlighted in bright red. Yours may be highlighted in a different color depending on your color choices. Maybe I can try to do it with 600 instead. Select again. Now I have fewer rivers highlighted. What if I pick a smaller number, like 6? Now all of my rivers turn red. So this is illustrating that the river sizes are already coded into that shapefile. We just have to pick the right threshold that collects the large rivers and the major tributaries, but not every little tiny river on the map. So this is sort of this is a subjective thing. You have to basically practice this for a while until you start to select the number that looks right for your particular situation. But the best piece of guidance that we can give is that you want to pick a threshold that highlights the major river and the major tributaries, not every little finger, but you also don't want to pick something so large that you don't highlight any rivers at all. So I already tested this example, and I found that a number around 400 worked pretty well. So I'm going to pick that, and sure enough, when I select 400, if I go to where my purple dot is where my gauge is located, and I trace that upstream, you'll see that in red I have all of the major river, and then a few of its big tributaries, but I've left off the edges of the basin, and that's exactly what I want for this step. So once I'm satisfied with that selection, I'm going to click Close. Now, I'm going to use my coordinate box again, and this time I'm going to basically try to draw a box around the edges of my river basin. So I'm going to trace upstream from the purple dot, and as I do, I go all the way up to the headwaters. And then I look at where my coordinate box says I am in those headwaters. And it says, in my case, negative 73.584, 5.284. Okay, so based on that point and my gauge location, that kind of gives me the corners of the box. But remember earlier we said that we want to make sure we pick a domain larger than our river basin so that the DEM and FDR generation process works. So we're basically going to round in such a way that we pick even numbers for the latitude and longitude edges, and we pick them such that they're bigger than our actual river basin. So on slide 41 of the PowerPoint, you can actually see kind of just a circle or a lasso drawn around the area of the river basin. And now you want to take that lasso and you want to draw a bigger box around the outside of it. So whenever you do that, like I said, let's just pick some nice round numbers to make our math easy. In this case, when I'm over at the left-hand edge of my river basin, I'm somewhere around negative 73.5 degrees of longitude. If I want to go farther and include extra area, how about I just round to 73 degrees? So we'll pick 73 degrees for the right edge. For the left edge, our gauge is located at negative 74.6. If I want to go further to the left, a nice logical number to choose would be negative 75. So on the left side, we'll have negative 75. The right side will have negative 73. On the top edge, up in the headwaters, I was at about 5.2 degrees north. If I go farther north from there, we can pick 6 degrees. And on the south edge, my gauge is located at 4.45, and I want to go far enough south to catch a little tributary that I'm circling with my mouse is at about 4.2. So let's go down to 4 degrees, and that should catch everything. The advantage of picking these edges is that they're much larger than the actual edges of the river basin, so we erred on the side of caution. They're also round numbers, so if we need to do any calculations on this later, it'll be very easy to do. We won't have to worry about the math so much. So let's put this into action. Let's go to the raster menu, projections, and then warp, in parentheses, reproject. And when I click on that, a new dialog box appears. And I'm actually going to go to select right next to the output file. You notice the input file is already W001. That's because it has to be a raster, and so the only raster we have open right now is our DEM. So output file, we'll click select, and I'm going to go to desktop EF5 training, examples, example 2, QGIS, and I want to save my file. You can save it as whatever you want, but remember you want to make sure you know what it's called later if you need to come back and fix something. So I'm going to call mine clipped.dem.tiff. And now notice that it's saving our file as a geotiff, not as a shapefile. That's because now we're dealing with a raster, not a vector. We click Save. We can leave most of the other stuff alone, but we are going to change no data values to negative 32,768. And then we're going to click this little pencil icon down at the very bottom that says Edit on it. And when I click that, everything at the top grays out, and everything at the bottom now can be edited. So I'm going to start typing into this text box, and this will probably be hard to see on the video, but you can actually start typing into it. You should be able to see exactly what to type if you look at the associated PowerPoint. And real quick, before I do that editing, there's one more thing I need to check, which is resampling method near. So now I'm going to click the pencil, and it should say warp overwrite SSRS EPSG 4326 R near, and then after that R near, I'm going to have a space, and then I'm going to type -TE -75 4 -73 6 -TR 0.02 space 0.02 space. Now, what I just typed here is some important information. You may recognize some of those numbers, -75 and -73. Remember, those are the edges we picked for our basin on the left and the right. And remember, 4 and 6 are the edges we picked on the north and south, or on the top and bottom. And then TR, that tells QGIS what resolution we want to use. And so this is in decimal degrees, and so we're going to pick 0.02 because that divides evenly into whole degrees that we picked. So this is where the math comes in. If we pick something like 0.15, we'd have to do math to figure out if that actually divides evenly into 2 degrees or not. But when we pick 0.02, we know that divides evenly. 0.02 also corresponds to a resolution of about 2 kilometers or so. That's appropriate for this size basin. If you were running over the entire continent of South America and you try to do 0.02, it might take hours for this to run. If you did this over a tiny little creek in your backyard or on a farm somewhere, and you pick 0.02, that would be too large. You would be working with such a small domain that you want to pick finer resolution. So the resolution is slightly subjective, and again, that's another thing where you just have to practice enough where we start to feel for what the real good resolution would be to use for a particular example. So we're going to click OK, And a little window will pop up and say processing completed, so you can click OK on that. And then QGIS bin, you can say OK on that, and then click close. And now you'll see my window has changed. Now I see black and white that's covering up all of my rivers. So I'm going to zoom out to see more of this area. And you'll see that we've created a box now. And that box is our DEM. That box is going to be also our model domain. Now, you want to right-click Example 2 Rivers, and you're going to go about halfway down the menu and go to Save As. And you'll get a dialog box that pops up called Save Vector Layer As. The first box says Format as a Shapefile. That's what we want. We're dealing with a shapefile, so we want to save it as that. And we're going to go to Browse next to Save As, and it's going to ask us where we want to save our file. In my case, I'm lucky. Now QGIS recognizes that I want to work in this folder, so I'm already in my good QGIS folder. I know that because I see Example 2 Rivers, I see Gauge Location, and I see other files and folders that look familiar to me. So I'm going to save this as large rivers.shape.shp, click Save, and I'm going to click some other things. They're highlighted in red on the PowerPoint. I'm going to click Save Only Selected Features, and I'm going to click Extent Current Layer. And I have some really nasty numbers in mind, like 14.84, 58, 33, and some other nasty stuff that I don't care about. What I'm going to do instead is I'm going to use the extents I already found. So the north edge or the top edge is 6, the south edge is 4, the west edge is -75, and the east edge is -73. These are the exact edges that we already used to create our DEM. This is important because we want to do everything on the exact same grid and location throughout the entire project. Now I'm going to click OK. And when I do, I get a little blue box at the top that says Saving Done, Export to Vector File has been completed. And I have a new layer called Large Rivers. So I'm going to unclick the X by Example 2 Rivers, and it disappears. I'm going to unclick the X by W001001, and I'm going to drag Large Rivers on top of clipped DEM. And mine's in purple, so it's a little bit hard to see. So I'm going to make it thicker. I'm going to go to Properties and bring it up to about 1.25 millimeters. And now, sure enough, you see the large rivers superimposed on top of the DEM I already created. So, just to take a second to review, you remember we set up our project, we filtered out smaller rivers, we used that information to determine the extent of our basin, we clipped the DEM to that extent, and we changed the resolution so that the model will run faster. We also saved our filtered rivers, and they're on the exact same extent as our DEM. Now we need to repair the DEM. When we change the resolution of the DEM, we tend to break things. We create pits and sinks that didn't exist in the original data and that aren't natural, that don't actually exist on the surface of the Earth. So in Processing Toolbox, you may recall that we dealt with TAUDEM earlier. I've used TAUDEM before, so mine's at the top and just recently used algorithms. So if you haven't used it before, you'll go down to the bottom to TAUDEM, click the plus sign, then to Basic Grid Analysis Tools, and then to Pit Remove. And remember, I just said that we might have created some pits and sinks. Well, now we're going to use TAUDEM to remove those pits and sinks. So I'm going to pick Clipped DEM for the elevation grid, and then I'm going to click the ... next to Pit Removed Elevation Grid. I'm going to go Save to File. A dialog box comes up, and you can probably guess what file or what folder I'm going to go to now. EF5 Training, Examples, Example 2, QGIS. And rather than test, I'm going to save this as corrected DEM.TIFF. And again, remember this is a TIFF because it's a raster file. This is going to be a grid. And I'm going to click Save. And then TAUDEM is going to open the output file after running an algorithm for me. So I'm going to click Run. And the dialog box goes away. And now I have a new file called Pit Removed Elevation Grid. And I'm going to move large rivers back on top of it again so I can see everything. So this Pit Removed Elevation Grid, it's pretty similar to the clipped DEM. The numbers changed slightly, and that's because the TAUDEM algorithm went through and fixed some of the pits for us. And so once the process is completed and that layer has appeared over in your layers window, you'll be able to burn our rivers into the corrected DEM. And we do this, we call it burning because we're actually sinking the rivers down, or sinking the river channels down in the DEM to make sure the model knows exactly where the rivers are located. So we're going to do this by going to the raster menu and then raster calculator, which is the top option. Oh, excuse me, first, before we do that, let's go to the raster menu and we're going to convert our rivers into a raster. So we're going to go to rasterize, vector to raster, and you want to make sure that you're selecting the right input file. So we want bar rivers. Attribute field in this case doesn't matter because we're going to change it later. Output file for rasterized vectors or raster. So this time we're saving it as a raster file, so it's .tiff again. And QGIS already knows what folder I'm in. I see clip DEM and corrected DEM, so I know I'm in the right place. I'm going to call this rasterized rivers.tiff. I'm going to click save. And it tells me the output file doesn't exist. You must set up the output size or resolution to create it. So we're going to do exactly that. We're going to click the pixel icon down at the bottom so we can edit this command. And I'm going to delete some of what's already here. I'm going to delete the A and ARC ID and TS 3000, 3000. It's going to go away. And I'm going to replace that with -burn space -10. So that's going to burn the value -10 into the raster in each location where a river exists. So that's going to mean that each river basically counts as -10, which will be important later. Then I'm going to do, so after -10 I have a space, then -TE, and I'm going to type -75, space 4, space -73, space 6. These numbers should look familiar. These are the edges of our basin that we've already used a couple of times now. Then after another space I'll have -TR and 0.02, space 0.02, and a space after that. And so this is creating a raster of all of our rivers. All of the rivers will have the same value of -10, and they'll be on the exact same grid and extent as our DEM. So you're going to click OK. You'll say processing completed, QGIS and done, OK, and then click close. And now you'll see that I have kind of blocky looking patterns on my rivers where I didn't have that before. So now we're going to basically add this river network to the DEM. And the way we do that is in the raster menu, we're going to go to raster calculator, which is the first option. So in output layer, the first thing we want to do is make sure we're saving our file. So I'm in my QGIS folder, I see clip DEM, corrected DEM, example 2, I know I'm in the right place. And I'm going to save this as burned_DEM.tiff. And you'll see that I already have xmin is -75, xmax is -73. All of this stuff is already consistent with the layers I've been using so far, so that's a good sign. I'm going to double click Pit Removed Elevation Grid, and it appears down at the bottom in Raster Calculator Expression. Then I'm going to type a plus sign, 2 parentheses, and an asterisk and a 3. And then I'm going to move my mouse inside the parentheses, and I'm going to double click on Rasterized Rivers. So this is basically just a math problem. Now I see DEM, or Pit Removed Elevation Grid, plus Rasterized Rivers times 3. And once I have that, you'll notice down at the bottom of Raster Calculator it tells me expression valid, so that's a good sign. That means I shouldn't get any errors. And I'm going to click OK. When I do, it looks like my DEM is back. And basically what we just did with this step is we lowered the elevation of every pixel in the river channels by 30 meters. This is also known as burning the rivers into the DEM. Now that we've done this burning process, we're going to be safe and we're going to remove the pits from this burn DEM one last time, just in case any errors were introduced in the burning process. But I don't want to get confused between my pit removed elevation grid, so I'm going to remove the old one. It's going to ask me, are you sure? Yes, I'm sure. So now I can go back to pit remove, back to Taudo. And this time for elevation grid, I'm going to select burned DEM. I'm going to do the ... save to file. And this time, I'm going to save it just as dem.tiff because this is going to be the final DEM we use for the example. So I'm going to click run. And now I have another pit removed elevation grid that's appeared. And that's going to be our final one. When I mouse over it, in fact, it tells me the file path is EF5 training examples, example 2, QGIS, dem.tiff. So one more time to review, we set up all of our project. We had the rivers, the gauge outlet, and the DEM to start with. That was our initial data. We used the gauge outlet and the rivers to draw a box around the edges of our basin. We resampled the DEM to a new extent and a new resolution, and then we used our filtered rivers to burn the streams back into that DEM while also removing the pits and any other errors. Now it's time to generate the flow correction and the flow accumulation. So these steps are a little bit easier, or at least a little bit shorter. We're going to go to TALDEM again over in the processing toolbox. This time we're going to open D8 flow directions. And for pit filled elevation grid, I'm going to select pit remove elevation grid. Then I'm going to click the ... by the flow direction grid box, save to file, and I'm going to call this one flow_dir, short for direction.tif. And again, this is a TIFF because it's going to be a grid, it's a raster. I want to make sure that I save it to my QGIS folder with all the other file names that I recognize. And now I'm going to click run. And when I do, if you look over at the left, you'll see some new things have been added to your window, including the D8 slope grid and the D8 flow direction grid. I don't need the D8 flow grid or the D8 slope grid, so I'm going to right click and click remove. And it's going to ask me, am I sure? Yes, I'm sure. And now you'll see I still have my D8 flow direction grid. I'm going to turn off burn DEM so that I can see my flow direction. It looks kind of weird, but don't worry, it's readable by a computer. Remember, this grid consists of numbers 1 through 8, and those correspond to the directions in which water is flowing across the domain. But we still need to do one more step to this. We want to convert it to a format that EF5 finds easy to read. So we're going to go to the raster menu, conversion, and then translate parentheses convert format. And when I go here, a little dialog box appears. Input layer this time needs to be D8 flow direction grid. The output file, you can go to select. It'll ask you where you want to save it. In my case, it's now defaulting to the QGIS folder, which is good. And I'm going to call this fdr.tif because this is going to be my final flow direction map that I use in the model. I'm not going to worry about too many of the other options, but I am going to go down to the bottom and click the pencil. And this time, in place of OF GTIF, I'm going to type, right after GL translate, I'm going to type -OT space float 32. So it should say GL translate -OT space float 32. And once I have that, I'm going to click OK. It'll say processing completed, OK. QGIS bin, OK, and then close. And this new FDR, it looks exactly the same on the map as the previous one did. We've just changed the format in which it's stored for EF5 to read it. Now it's time to create our flow accumulation map. We're going to do that by going back to TALDEM over on the right-hand side of the window. And this time you're going to click on the first option, D8 contributing area. I get a new dialog box that comes up. It's going to ask me what my flow direction grid is. So this time we'll pick FDR. We don't need an atlas shapefile. We don't need a weight grid. We're going to go ahead and leave edge contamination checked. And we just need to tell it where to save the file. So use the ... out at the edge. It'll open up to the QGIS folder, in my case, where everything else is stored. And I'm going to save this as fac.tif.tif. This is my final flow accumulation grid that I'm going to use in the model. I'm going to click run. And when I do, you'll get something that looks awfully dark. And we're going to make sure that it looks right. So I'm going to turn off the rivers, but I'm going to leave my gauge network on. And this is a good sign. This is exactly what we want to see. The areas in black are overland cells with not much flow contributing to them. The areas in white have higher values and have a lot of flow contributing to them. So the wider the value gets, the larger the river is getting. And it looks natural as we progress from the upstream areas of the river. It goes from black to gray, then down into white. It's also good that I don't see any breaks or any weird stuff in my river. Everything upstream of the gauge location looks just fine. I can even see the little tributaries coming off of it and fading away. This is a really good sign. You can turn on the river's shapefile again and make sure that the white pixels follow the outline of the rivers, and for the most part they do. They don't catch every single bend and crease and crick in the river, but for the most part they get it right, and that's all we really want, is to get it close. So we know from previous research that the drainage area of Bogota at Puente Portillo is about 6,000 square kilometers or so. And we want to check and see how close our value gets to that value. So the way I do that in QGIS is I go up to the top toolbar and I click the blue eye with the mouse on it called Identify Features. And when I click that, I get a pane that appears in the bottom left of my screen called Identify Results. I'm going to go down to the bottom of that and change the view from tree to table. That'll change things again for a second. And then I'm going to click on a pixel somewhere around my gauge location, but not exactly on my gauge location. I'm going to pick one of the white pixels. And when I do, it's going to give me a list of things to choose from. And I'm going to choose the D8 flow direction grid. And when I click, then I go over to Identify Results, and I scroll to the side. And I'm going to click Contributing Area Grid. I'm sorry. And I get a value, in my case at least, of 1,122. If you click around, you'll get 1,112, 1,075, some different values depending on exactly where you click. And that means that that many grid cells are contributing to that area. Now, if you recall, each grid cell in this domain is 2 kilometers on the side, or 4 square kilometers for each grid cell. So if I multiply that value that I get by 4 square kilometers, I'm going to get something in the neighborhood of 4,200 to 4,400 square kilometers. Remember that the actual drainage area of this basin north of the gauge location or upstream of the gauge location was around 6,000 square kilometers. So we're losing a little bit of the area due to processing the DEM and changing some other things. But for the most part, this is the range that we want to be in. If you do this and you get a result of like 2 or 12 or 20 or even 100, that means you've done something wrong and you need to go back and follow through all the steps again. But just visually, from the way that the river network looks connected and it seems to follow our shapefile, and also from the way that the values seem to be relatively reasonable and what we'd expect, that means that we've probably done a pretty good job and we're ready to use these files in the model. So you've saved your QGIS project before, but now let's save it again. So just click the little disk icon up at the top of the screen. And now we're going to exit QGIS. We're done with QGIS for now. And I still have my QGIS folder here open on my desktop. And I have a whole bunch of files in it. Now, if you remember, just a few minutes ago when we started this video, this folder was totally empty. And look at all the stuff we've created now. In my case, I have a total of 39 items that have been created. But out of all of these, there's only a few that I really, really need. That's fac.tif, fdr.tif, and dem.tif. So I'm going to move this QGIS folder over to the side of my screen. On the other side, I'm going to go to EF5 training, examples, example 2, basic. And my basic folder is empty, and I want to fill that basic folder up with the things I need to run the model. So I'm going to do Control-C, or you can right-click and go to Copy on dem.tif, and I'm going to paste that over, not a shortcut, sorry. I am going to right-click on dem.tif, and I'm going to paste it, not paste shortcut, but just paste. I'm going to do the same thing for the flow accumulation, and then finally for the flow direction. The reason why it's important to copy rather than just move is that it's nice to keep the original files in your QGIS folder. In case something goes wrong later, you'll be able to go back and you won't lose all of your work. You'll be able to just start from that point, since you've at this point already generated a good DEM, a good FAC, and a good flow direction map. Now we're going to go to EF5 training, examples, example 2, and I'm going to open up my control.txt file, and I'm going to make sure that it accurately reflects what's actually in my basic folder. So it's saying DEM, the second line there is basic/dem.tif. And sure enough, that's exactly where I just moved the DEM file to. Same thing for the DDM, it's pointing to fdr.tif, and the FAM is pointing to fac.tif. So everything there looks good. Some of the other options here that we want to keep in mind, the projection line that says PROJ equals geographic, that's telling EF5 that all 3 files are in the geographic projection. And we know that they are because geographic projection means that we use latitude and longitude. And that's exactly how we found the edges, that's how we found the gauge outlet, and all of that. So we're using geographic projection, so we're going to leave that alone. Esri DDEM equals false goes back to the coding scheme that we talked about in the beginning of this module, which is the flow directions are either 1 through 8, or they're 1, 2, 4, 8, 16, on up to 128. The ones that go up to 128, those are used by Esri. The ones that go up to 8 are used by Towden. So we're not using the Esri scheme. We're only going 1 through 8 because we use Towden. So we're going to leave this as Esri DDM equals false. And then finally, self-FAM equals true means that the lowest value of any cell in the FAC is 1. In other words, that means that each cell counts itself as contributing to itself. And so you could test this by going into QGIS and looking at the layers panel, and it'll show you the minimum and maximum value of your flow accumulation grid. And you'll see that the minimum value is 1. So we know that self-FAM is true because we're counting each cell in its own count. We're going to do a little bit more file copying. You can go ahead and exit the control file. We didn't make any changes, so you shouldn't have to save it. And we're going to go to EF5 training. And I have 2 windows open, so I can do it in either. And I'm going to go to Data, Observations, and you see this CSV file, puenteportillo.csv. I am going to copy this. In your case, you can move it if you want. And I am going to send it to example2 obs. So I'm going to right-click and click Paste. And now Puente Portillo is in my obs folder. If you want, you can use Microsoft Excel to open up this file. And the reason why we want to do this is to make sure that it looks like what we expect it to look like, and also so that we know what it's supposed to look like. And you'll see it's blank at first, but I need to go down to the bottom. You might remember this from earlier, and I need to make sure that we can also open CSV files. So I'm just going to click All Files, and now it appears. I'm going to click Open. And now I have some data. The data I have consists of date and then a mean queue, or mean stream flow. And so it's important to note that this is the format that EF5 likes. It likes to have a column with the date and time, and then another column with the stream flow values. There are a few things that you need to keep in mind. One is that EF5 needs to have the date format be in one of a few certain ways. So it can either be the year, month, day with slashes in between, and then the time with colons in between, or you can have dashes in between the dates. You have just the dates. But you need to make sure that you have the year, the month, the day, and then if you prefer, you can have some type of information about the time or not. All of the available time and date formats for observation files are on either slide 67 of this module, or they're also available in the EF5 README folder, the EF5 README file, excuse me. So at this point, I'm going to go ahead and exit Excel, and I'm not going to save because I didn't change anything. We've added files to our basic folder and to our ops folder. We also have an output folder. That's not going to be filled yet because we haven't run the model yet, so there's nothing for it to see. And so really all we have left is ET and precip, and we're going to fill those in the next module, which is module 2.1. And so that includes module 1.4. We hope that you'll come back and join us for rainfall and PET, which is module 2.1. And we'll get those folders filled, and we'll get one step closer to running the model with all of these files that we just created. So thank you very much for watching. If you want to look into any of the module 1.4 references, we have a couple of basically training documents or checklists that show you just real quickly what the properties of the various example basins throughout the training are. We also have the checklist that goes through step by step with all the stuff in QGIS and the other related programs. And then there's also a paper from Jensen and Dominin. I'm not sure how exactly to pronounce that, but Dominin, I think it is. And they tell you how to extract various information from DEMs, basically following the process we just did. So we'll see you in the next module.